Hi, welcome to my talk. My name is Dennis Bodewits from Auburn University, and I was asked to give a review about X-rays in the solar system. Since you are here, you're obviously interested in solar system X-rays, and I'd like to advertise that we have an open postdoc position here at Auburn University. This position concerns the modeling and observations of cometary X-rays, and therefore the atomic and molecular processes that occur in cometary atmospheres. We have observations in hand of Chandra, XMM, Swift, NICER, which is a new telescope on the space station, and Suzaku. And for more information, send me an email at dennis@auburn.edu. So this is a brief overview of my talk. Solar system X-rays are very interesting because they sample a very broad range of environments and therefore of astrophysical processes that occur. In our solar system, you of course have the sun, but you also have rocky planets, some with atmospheres, some without atmospheres, as well as the giant planets with, which provide extreme conditions in terms of magnetic fields and radiation environments. Also, the solar system provides many unique opportunities. We have space missions actually that fly to those objects and that can sample local conditions. And at the same time, remote observations can provide the large-scale context by which the X-rays are produced. Planetary observations also provide the opportunity to study orbital variations. For example, comets move on these extreme elliptical orbits, or seasonal variations as planets orbit the sun. The sun itself also has various variations at very different timescales, as we'll see, minutes to years. And then finally, the solar system provides what we'd like to call opportunistic events. Objects collide, objects may go into outbursts, or once in a while, objects may have a very favorable alignment that allows you to study in a way that was not possible before. So here's a brief overview of solar system X-rays and the mechanism responsible for it. I will not be able to go through all of them today in detail, and of course this is always in flux. Notice the big barcode on the right. I've made this this table available to Google Drive, so just follow that link, obby/solar system, to see this, and you are allowed to leave comments if I get to make this overview more complete. So in the leftmost column, you see the name of the object and approximate distance from the sun. I explain what is the emitting region. There's a rough estimate of the total power output, the luminosity of the objects in X-rays, and the brief summary of mechanisms that have been identified that may be responsible for that emission. And the abbreviations are explained in the legend down below. So in very brief, you can see that there's an enormous range of X-ray luminosities going from 10 to the power 20 watts from the sun down to about 1 megawatt here for Mars, and all of those are highly variable. So let's start with the sun. The sun is actually the source of all the X-rays that come from the solar system in one way or the other. The sun itself here is shown in this image is a combined image by NuSTAR and the Solar Dynamics Observatory. And so in green, you see the hard X-ray detection by NuSTAR, 2 to 5 kiloelectron volts, or equivalent to temperatures above 3 million kelvins. And in red, the very detailed background image is acquired by SDO at 171 angstroms, equivalent to about 1 million degrees Kelvin. X-rays from the sun come from the corona, the outermost part of the sun, and are caused by both Bremsstrahlung and collisions between ions and electrons. So the flares are a clear source of variation of solar X-ray fluxes, and they occur at timescales of about 10 to seconds of minutes. Another source of variation is the solar cycle, which results in X-ray variations at timescales of about 11 years. The sun is not only a source of X-rays, it is also a source of a stream of highly charged ions, the solar wind. The organization of the solar wind is shown in the panel here on the left. During solar minimum, the solar wind is organized in an equatorial wind with a velocity of about 300 kilometers per second, and a polar wind with a velocity of about 700 kilometers per second. The solar wind at equatorial latitudes has a wind that comes from on average higher coronal regions, and therefore has more heavy ion content than the polar wind, which comes from cooler regions and has less highly charged ions. During solar maximum, this neat organization disappears, and as you can see in this image here, the solar wind is simply unorganized, and also you'll have multiple coronal mass ejections and flares on every day. So on this tour of the solar system, we will go further and further away from the sun. So the first planet to interact is the rocky planet Mercury. At this moment, there's a small spacecraft named Bepi Colombo, flown by the European Space Agency, which actually carries an imaging X-ray spectrometer that is sensitive from between about 0.5 to 7.5 kilo electron volts. Plans are that that Mercury will be orbited with pretty complicated elliptical orbits, starting at about 500 kilometers above the surface. And this X-ray spectrometer will be used to characterize the elemental composition of Mercury's surface. So why does Mercury emit X-rays? Mercury emits X-rays through fluorescence of solar X-rays by surface minerals. And that process is shown here. What you have is you have incident solar X-ray photons coming in that will interact with your heavy atoms and result in the ejection of K-shell electrons along with X-rays. More about this instrument is given in Bond's et al. 2020. Bepi Colombo is supposed to arrive at Mercury in about 2025. The same process occurs on asteroids. Asteroids are also rocky bodies. I'm cheating a little bit because those bodies are mostly found between Mars and Jupiter, but the process is very similar. And an X-ray imager was actually carried aboard on OSIRIS-REx, which the mission that just samples part of asteroid Bennu. No X-ray detection of the asteroid was found, but they did actually detect some astrophysical sources behind it. Our next planet is Venus. Venus does not have a magnetic field, but it has a very dense atmosphere. And X-rays from Venus were first discovered by Konrad Dennerl in 2001. And that's the image that is shown in here. So you can see that it is a sparse detection. Observations of Venus are very hard because it's an optically very bright object, as you all know. If you've looked up in the sky, it is often the brightest object that you can see if you look at the right times, but not so in X-rays. When it was first observed, it was during solar maximum, and the main process responsible for the X-ray emission was fluorescent scattering of solar X-rays. So carbon and oxygen atoms absorb X-rays emitted by the sun and re-emit them at specific wavelengths. And what you can nicely see, even though there are not a whole lot of X-rays coming from it, is this nice pattern of solar limb brightening, which indicates that the X-rays are coming from the atmosphere and not from the surface, which would be optically thick. Now, Konrad Dennerl did a really nice experiment where a couple of years later, he went back to observe Venus, and he did this during solar minimum. So when the sun emits a lot less X-rays. And by carefully selecting the wavelengths on which different processes emit, he was able to create images of Venus in first charge exchange emission on the left here, and then in the fluorescence emissions, which I just explained to you on the right here. So charge exchange, I mentioned before that the sun emits both X-rays and highly charged ions in the solar wind. And the solar wind is a plasma that originates from an environment from between 1 and 2 megakelvins, a million Kelvin in the corona. It's a collisionless plasma that expands through the solar system at about 250 to 1,000 kilometers per second. And remember the highly variable timescales correlated to the sun. When these highly charged ions interact with neutral atoms or molecules, as shown here, they will capture one or more electrons from that neutral particle. This electron can be captured into an excited state in the incoming ion, and when it when this electron then falls back to the ground state, we want more photons are emitted, typically at soft X-ray wavelengths about below 1.5 kilo electron volts. Charge exchange emission is characterized by mostly forbidden lines, specifically of the oxygen 7 and carbon 5 lines, and that's how Konrad Denner was able to separate the charge exchange emission from the fluorescence emission. So this is mostly oxygen 7 emission at the forbidden line. Going to Earth. Earth is a more complicated environment because we have a magnetic field, and this magnetic field results in the acceleration of electrons that then produce electron bremsstrahlung, as shown in this image acquired by Chandra over here. At harder wavelengths, the Earth atmosphere also produces X-rays by the Thomson scattering of solar X-rays by electrons. And what you see is mostly fluorescence, also from nitrogen, oxygen, and argon. And this is an image acquired by the PIXI instrument. There's another part which is very interesting. So what you see here is X-ray observations by ROSAT of the moon. The sunlit part of the moon is shown on the right here, and this is bright because of the fluorescence and reflection of X-rays, just as we saw for Mercury and the asteroids. Notice that, however, also for the dark side of the moon, there are still X-rays detected, albeit at a lower level than the background X-rays that you see here. And so what happens there is that these X-rays are produced by solar wind charge exchange with the exosphere of Earth. So the tenuous part that mostly consists of atoms further away from Earth's atmosphere. There are currently 2 missions being prepared that will use this emission to study the interaction between the solar wind and Earth. So the first one is a collaboration between the European Space Agency and the Chinese Space Agency. It's the Solar Wind Magnetospheric Ionospheric Link Explorer, or SMILE, which is supposed to be launched in 2025. A smaller satellite is prepared by Boston University in collaboration with NASA Goddard and several different partners. That's called the COSPAR Plasma Imaging Detector, or CUPID, and that's supposed to go up next year. Next on our planetary tour is Mars, and the X-ray emission of Mars is very interesting. First, on the left here, you see an image again made by Konrad Denner using XMM Newton observations of Mars. The yellow parts there are fluorescent emission from Mars's disk, whereas the green, blue halo around it are the product of charge exchange emissions in Mars's exosphere, which of course consists of atoms that are escaping from Mars as Mars continues to lose its atmosphere. This could be investigated by high-resolution spectroscopy, as shown in the 2 panels to the right of this. First of all, in the middle here, you have the spectrum of Mars's disk, which is dominated by very strong fluorescence lines owing to CO2 molecules. So this is line 9 and 10. Notice that lines in 6 and 8 are your traditional oxygen 7 lines, and notice that here that the resonance line is much stronger than the forbidden line. The resonance line would be indicated by 6, the forbidden line is indicated by 8. Now, when you look at the spectrum of the halo, you immediately notice that those strong CO2 lines are not present because in Mars's exosphere, you only have atoms produced by the photodissociation of those molecules. But when you also look again at lines 6 and 8, you notice that their relative strengths have now changed. Whereas now line 8, the forbidden line of oxygen 7, is much stronger than the resonance line. And that is your typical signature of charge exchange. So comparing the spectra of Mars's disk versus its halo, you can see that the outer atmosphere of Mars is dominated by charge exchange. Next up in our total solar system is what may be one of the most complicated environments, Jupiter. Not only is Jupiter a gas giant, it has an extreme radiation environment and multiple processes that lead to highly variable X-ray emission. And I really recommend that you listen to the talk by William Dunn, also in this session. So on the left, you see the aurora on the North Pole. On the south, those on the right, those on the South Pole. And the aurora are caused by oxygen and sulfur ions that are accelerated by Jupiter's magnetic field and precipitate into its lower atmosphere. And this emission is typically variable at timescales of 10 to 60 minutes. At lower latitudes, the X-ray emission is likely dominated by scattered solar X-rays. I will not talk much about this, but several of the Jovian satellites, the Galilean satellites, have also been observed in X-rays, most notably Io, which is an extreme volcanically active little moon, and Europa, which of course is one of our prime astrobiological targets of interest. Further away, we have Saturn. Saturn has mostly been detected in scattered X-rays. It's a relatively faint target and really hard to do. Jan Oudnes made this beautiful composite image where you see the Chandra X-ray images of Jupiter on the left versus a Hubble image on the right. There is evidence that we also have reflected X-rays from the Saturn's rings. And one of the most interesting experiments that were done by on Saturn is from this paper by Neil Bartway in 2005. So what you have on the top is the X-ray signal of Saturn as a function of time. These indicate hours, and at the bottom you see the solar X-ray flux as a comparison. And so what happened is that as the sun underwent a bright flare, this flare was also detectable in X-rays from Saturn. So again, confirming that Saturn is mostly emitting X-rays through scatter processes. Total brightness luminosity of Saturn is about 25% of Jupiter, and that's right where you would expect it, as this object is about twice as far from the sun as Jupiter is. Next in our tour of the solar system, we get to look at comets, and those that are familiar with my work will not be surprised that this is my favorite part of the talk. So when you look at a comet in X-rays, this is about what you see. This is an image that was painstakingly acquired by the Neil Gehrels Swift Observatory, which has both an X-ray telescope and an ultraviolet telescope on board. And they're always used at the same time. This Swift looked at Comet Lulin, which was a very bright comet of about 7 magnitudes, which is about the brightest that Swift viewer can observe. And in ultraviolet wavelengths, it observed, and that's indicated in blue in this image, the cloud of hydroxyl radicals surrounding the comet. Hydroxyl is produced by the photolysis of water. In red, you see the X-rays, and what you notice is that the shape, the morphology of the X-ray emission is completely different from that in blue, the neutral molecules. The reason for that is that cometary X-rays are produced by charge exchange, which we encountered before, and so you have these solar wind ions coming from the bottom left here, interacting with your cometary atmosphere. They become neutralized. The coma is collisionally thick to charge exchange, so at a certain point, you no longer have any ions that can produce X-ray emissions. You could consider this like an umbrella seen from not exactly the side, but more like on a 45-degree angle. So you're depending on your viewing angle, you could see this umbrella from the side, in which you would get like a crescent shape, or you can see it from the front and you see a circular shape, or anything in between. So why am I so excited about cometary X-rays? Now, comets really provide you with very different environments. They move around the solar system just any way they seem fit. You can observe them at different heliocentric distances. You can observe them at different heliocentric latitudes. And because of that, they can sample different parts of the solar wind. Remember that we started with an overview of solar X-rays and the solar wind parameters. And again, at solar minimum, your solar wind is organized in low ecliptic latitude and high ecliptic latitude solar winds. And comets are the only objects in the solar wind that can sample both. Your planets are just going to stay in your ecliptic plane. At the same time, comets also have a very broad range of activity levels. Comets are chunks of ice and dust, and when you heat them with sunlight, the ices in comets will start to sublimate. This is at a broad range of levels, from just merely tens of kilograms of material per second up to the hundreds or thousands of kilograms of material per second. And depending on this, your cometary atmosphere, or coma, will become collisionally thick or thin to solar wind charge exchange. Comets thus provide an analog to different planetary atmosphere conditions. Another reason is that comets are extended sources as opposed to the planets. So it allows you to really study different plasma interaction regions. Furthermore, comets are ideal for studying temporal variation and therefore as natural laboratory. Comets undergo outbursts where their activity suddenly ramps up by a factor of 10, or comets are also then, of course, exposed to solar wind variations. How do you study this? Spectroscopy. And what this yields you is, first of all, solar wind origins. So by measuring cometary X-ray spectra, you can determine freeze-in temperatures of the local corona from where the solar wind originated. You can study forbidden lines because cometary atmospheres are so thin. This is something that it's very hard to study in the lab because of the long lifetimes of the metastable states of the heavy ions responsible for X-ray emission. It may even be possible to use X-rays to study the neutral chemical composition of comets. Two examples that we saw before, the Mars disk, you had fluorescence of carbon dioxide, which was one of the brightest emission features. Also in the halo of Mars, we saw that the spectral line ratio between the Lyman alpha and the higher order, the K alpha and the higher order lines, depending on the target species of choice. And so cometary X-rays may provide a way to study the chemical composition of cometary atmospheres, specifically of elements that also are not so easily sampled otherwise. And as we'll see, an open question is still what the role of cometary dust plays in the formation of their X-ray spectra. To explore some of the diagnostics that cometary X-rays provide you, I'll walk you through an example of X-ray emission by Comet Tempel-1, which was the target of NASA's Deep Impact mission in 2005. To demonstrate a little bit of the rich diagnostics that cometary X-rays provide, I show you here an example of the X-rays of Comet 9P Tempel-1. 9P Tempel-1 was the target of NASA's Deep Impact probe. This probe shot a copper bullet into the nucleus of Comet 9P. The result of that is shown here, in order to excavate some of its material and study cometary materials below the surface. So in this plot, and there's a lot of information there, but I'll walk you through it. So what we have here on the x-axis is time, as in units of day of year of 2005. So this was all around the middle of the year, so July of 2005. The lowest plot here shows the behavior of the comet in optical wavelengths, and so it's a proxy of its gas production rate. So how much neutral gas is produced by this object. You can see that around day of year 182, the comet had an enormous outburst, shown by this deep impact image here, where its brightness increased by a lot. Activity was mostly quiescent, except for this period here, where the comet was hit by a deep impact probe. And again, the activity ramped up for a short while. At the same time, we also looked at the solar wind flux as measured by SOHO and ACE, two probes at the L1 point. This is the flux, so it's the product of the proton density and the proton velocity. And you can see that there's an enormous variation during the deep impact mission. Most of all, notice this big increase here, which is caused by the arrival of a big coronal mass ejection that was released from the sun on 7/13, an image here by SOHO that was estimated to arrive at the comet at this period. Now, by simply taking the product of the solar wind flux and the comet gas, you get sort of a prediction of how much X-rays you would expect from this object. And that's shown here. So in black, you have X-ray brightness measurements acquired with Chandra, and in blue, you have X-ray acquired brightness measurements acquired with Swift. And you can see that for most of these curves, the predicted X-ray brightness follows the product of the solar wind flux and the comet gas quite nicely. Also, from our experience, it is the solar wind variability that drives variation in X-rays the most. And unfortunately, that makes cometary X-ray brightness a little bit unpredictable. Next up, spectroscopy. I want to show you here the results of the Chandra Comet Survey that I conducted in 2007. So if you have a cometary spectrum, you can essentially divide the spectrum in 3 bands, and they're indicated with different colors here. So there's the darker blue, the lighter blue, and more of the red here, and those coincide with the emission of carbon and nitrogen ions, here with oxygen 7 and there with oxygen 8. And how these plots are organized is that the plots on top here have the strongest carbon and nitrogen bands, and the plot at the bottom here has the strongest oxygen 8 bands. And that essentially correlates exactly to the solar wind freeze-in temperature. So on the left here, you have a plot of the ratio of oxygen 8 plus ions to oxygen 7 plus ions as a function of the freeze-in temperature shown in here. And all those dots refer to different comets in this plot here. And you can see that in the different color bars here, I indicated the different regimes that you can have in the solar wind. The regular solar wind is your slow solar wind. That's the typical solar wind in the equatorial plane. You have the fast solar wind here, which is your solar wind at polar regions. And you have 2 more extreme regions, which is one, a hot solar wind at temperatures of above 2.1 million degrees at the source region, which are likely indicative of coronal mass ejections. And you have a very cold solar wind regime below 800,000 kelvins, which are more indicative of sort of coronal holes. So why don't you see any measurements in here? Well, when you are in these conditions, you're actually going to get very few of the solar wind ions that are required to produce solar wind X-rays. And that's illustrated in this plot over here on the right. So what you see on the right is a plot with, on the x-axis, you have the freezing temperature of your coronal plasma in kelvins. It's a logarithmic scale going from 10 to the power 5, so 100,000 kelvins to 10 million kelvins. And then on the y-axis, you have your ion fraction. So what are the predominant ions given for a certain temperature? So, and then the different shaded areas here indicate again your typical solar wind freezing temperatures for different conditions. So you see that for regular slow solar wind conditions, so the equatorial solar wind, you have a significant population of oxygen 7 plus, a small population of oxygen 8 plus, and a lot of oxygen 6 plus. Only oxygen 7 plus and 8 plus will emit in X-rays. When you go to coronal mass ejections, you're going to get much more oxygen 7 plus and 8 plus, but when you go to polar solar wind or the solar wind from coronal holes, all of your solar wind is in oxygen 6 plus and none of it in the higher charge states. So you're not going to produce any X-rays. Instead, you'll produce extreme and far UV emission, which cannot be detected by instruments like Chandra. Similarly, when you look at carbon, for your slow solar wind, you're going to have carbon 5 plus and 6 plus, both of which were contained in this band. And so what you see that in between, unless you get to really cold solar wind conditions, you will always have both carbon 5 and 6 plus. And all that you do is that you just move in X-ray energies a little bit lower, but overall your band here doesn't change much. So that explains this figure that by going to higher solar wind freezing temperatures, the relative amount of oxygen 7 plus and 8 plus is going to get stronger and stronger, which is indeed what you see here. So back to our tour of the solar system. Of course, our distant minor planet, Pluto. So Casey List and his team worked on the New Horizons team that flew by Pluto and simultaneously acquired X-ray observations with Chandra. And lo and behold, they found about 8 photons before background subtraction that were clearly correlated with Pluto. And the image is shown here. You got, of course, the beautiful optical image acquired by the New Horizons spacecraft with Pluto's heart. And this is a not-to-scale X-ray image of those 8 photons. This corresponds to about 200 megawatts, and that is a surprisingly large number. Comets, for example, which have similar gas production rates as Pluto, are between 100 and 1,000 megawatts. So here you have Pluto at the edge of our solar system, which is as bright as some of the fainter comets that we observe at about 1 AU. So what drives these X-rays? So Pluto does not have a magnetic field. The spectrum, if you can call it that, with only 8 photons, is not consistent with solar X-ray scattering, and it's way too bright for charge exchange. This is an open question, and if you think you have the answer, we're very happy to hear it. Is that you are now so enthusiastic about it that you would like to provide us with an X-ray instrument that would make us very happy. So what would be our wish list for a solar system X-ray instrument? First of all, we really like to have the high spectral resolution. As I've shown you with the studies of Mars and Venus, this allows you to pick apart different processes that will result in this emission and or tell you something about the chemical composition of objects that you study, like in the case of comets. Different from most astrophysical sources, solar system sources are rather soft X-ray sources, so we really like to have sensitivity around and below 250 electron volts. Solar system objects are moving, also moving on the sky, and currently X-ray telescopes are not most X-ray telescopes are not capable of tracking. Tracking would greatly help at sidereal rates, would greatly help with acquiring solar system objects. It allows for less overhead, for more time on target. Next up is background observations, and that's a funny one. As you've seen, emission from Earth geocorona is caused by charge exchange, and its emission is very similar to that of the objects of interest. And not only that, it also varies in time. So in order to study solar system objects, you actually have to dedicate significant time to acquiring a good X-ray background. And this is very relevant, particularly for extended sources. Next up, many solar system objects are bright. Think Venus, Jupiter, which are naked eye objects, and you really need a good optical blocking filter. Target of opportunity. I've mentioned that solar system objects can have many interesting short-lived events. And so what you would like is a telescope that has very agile operations and that can be on target in less than days. And that allows you to schedule perhaps observations along with space mission operations that could be of interest to you. Monitoring. Solar system objects likely vary as a function of time, and there are unanticipated events. So if you want to capture those, it would be great if you can just observe for an extended amount of time, corresponding to certain properties of your object. That can be rotational periods, seasonal effects, or typical time spans of solar transient events. And then finally, and that's a pet peeve of me, astrophysical observations are archived along with their coordinates. And if you have a solar system, their coordinates change as a function of time. And so this is not a good way to retrieve archival data of solar system objects. So maybe something that is name-based would really help us. This is the end of my presentation. Thank you very much for your attention. And I'm always happy to answer any questions. You can reach me again at dennis@auburn.edu.